All right, guys, so here we are with the Chapter 10 test review. Again, this is about the correlation and regression. I should say linear correlation and regression. So once again, these problems are due Monday, the first day of finals week, and they're worth 2 bonus points. So our problem statement says, when water flows across farmland, some of the soil is washed away, resulting in erosion. Researchers released water across a test bed at different flow rates, so it's water flow rates, and measure the amount of soil washed away, or the amount of eroded soil. The following table gives the flow in liters per second, so there are units, we might want those later, and the weight in kilograms of eroded soil. Okay, so here's our table. So just by looking at it, I can tell that the flow rates are increasing. And as the flow rates are increasing, it appears the amount of eroded soil is also increasing. So I'm already kind of thinking there's a relationship between these. Let's go ahead and enter the data into StatDisk to see if we can find one. Obviously, whenever we have two variable data like this, right? This isn't just from two samples measuring the same thing like we had in chapter 9. This is two totally different variables, flow rate and amount of eroded soil, okay? And they're paired, of course. This flow rate goes with this amount of eroded soil and so on and so forth. Whenever we have something like this, we're already thinking, oh, I could make a scatter plot and see if there's a relationship. Could calculate the correlation coefficient if the scatter plot appears linear and see just how linear the data is, just how correlated they are. And then I could describe my relationship, which is what part A asks us to do. It makes sense to do that. And then if it does appear linear, we can go ahead and find a regression line and make predictions based on that. So, okay, part A says use StatDisk to look at a scatter plot. We don't have to sketch it. We're just gonna look at it and find the correlation coefficient R for flow rate and amount of eroded soil. And then we're going to describe that relationship using that SDFU acronym. Remember, that's strength, direction, form, and unusual features. Okay, so first things first, I've got a new StatDisk page here. And in the sample editor, I've entered the flow rate in column 1 and the amount of eroded soil in column 2, making sure that they're lined up appropriately. 0.31 is matched with 0.82. Okay, so now I want to see a scatter plot. So one way I could do that is to go to Data and come down to Scatter Plot. I have to tell it the column that the X value is in. Now, flow rate explains amount of eroded soil, right? It's my flow rate that if I change my flow rate, I think it's going to change the amount of eroded soil. So I'll put my explanatory variable on the X-axis, the horizontal axis, and then my response variable, column 2, the amount of eroded soil on the vertical axis, the Y value. I could make a title and give X and Y labels, but I'm not going to mess with that for right now. And of course, I don't want to show the regression line yet. I'm not ready for that. Okay, so let's plot it. All right, I only have 5 values, so it's a little bit difficult to tell. But if I were to, let's say, use my pencil to be the least squares regression line, looks like it covers up all the data points, right? A line would fit nicely through those data points. And it again appears that the relationship is positive because as we go from left to right on the X-axis, the values appear to be going up, okay, positive direction. I'd say that they're fairly correlated, right? They look like a pretty straight line if I were to draw a line through there. So I'm thinking R is going to be positive and closer to 1. Let's see, what else can I say about this? The strength, direction, form, and again, the form appears linear. I don't see any like super obvious outliers. It's possible this dot up here, the 3.75 flow rate with the 6.07 amount of eroded soil could potentially be an outlier, but it is an outlier in the pattern. Okay, so let's go ahead and now find the correlation coefficient. So we have to go to analysis, which apparently still doesn't want to click correctly. There we go. Okay, analysis and then correlation and regression. So again, I have to tell it the X and Y variables, X value is 1, Y variable is column 2, and we don't mess with the significance, so we'll evaluate. All right, so we come over here and see our correlation coefficient R is 0.96698. That's a very strong correlation value. And we can also come up here at the top, instead of clicking on results, we can be on scatter plot. And now we can see that least squares regression line running through the data. Again, it does look like it fits that line pretty well. Going back to results, I noticed that I also have my regression results on here, but part A just asked for the correlation coefficient R in the scatter plot, so that's all I'm going to worry about right now. Okay, so let's think about how it is, again, that we're supposed to describe the relationship. I've got my IS number 22 notes here, reminding me of how I should describe the association with strength, direction, form, and unusual features. So my strength, my R value is very close to 1, so it's very strong, positive, linear, and I do not see any clear outliers. So that is what I'm going to say. Okay. I'm going to say there appears to be a very strong, that's my strength, direction is positive, form is linear, very strong, positive, linear relationship between, let's see, flow rate and amount of eroded soil with, and this is where I mentioned my unusual features, with no clear outliers, right? There's nothing that's super obvious, but maybe 3.75, 6.07 is an outlier in the pattern. Now, I will say again that scatter plots are subjective. We need further methods to really determine whether this is truly an outlier. We haven't learned those. So we're not going to make a clear determination about outliers. If you had just said no clear outliers, that would have been fine. If you had said maybe there's an outlier at this point, that also would have been fine. Okay. What you should be able to tell is that since R, I was supposed to find R, I better write down what R is. R is 0.966, what was it? 0.96698. Okay, since that R is so close to 1, we know that it's very strong. R is also positive, so we know it's positive, and by looking at the scatter plot, we can tell that it has a linear relationship. Okay, make sure again you also put the context in there. So part B says use StatDesc to find the equation of the regression line, and be sure to write the equation in context. We've already done the correlation and regression analysis on StatDesc, so we just need to look at our results here. So remember, B0 is the y-intercept, B1 is the slope. So we're going to fill in, what is it, first we want y hat. Remember, y hat is the predicted y. So I could write that, and I think this is what you'll be tempted to do, is write the equation using x and y. So y hat is equal to 0.40573 plus the slope of 1.38905x. But you would not get full credit here, okay? You have to use the context. So remember, my explanatory variable is x, it's my flow rate. And then my amount of eroded soil are my y values, my response variable. So notice I put y here because these are the actual amounts of eroded soil, but it's y hat here because I use this equation to predict amounts of eroded soil based on given flow rates. So the amount of eroded soil hat. You could also write predicted amount of eroded soil, I'm fine with that too, is equal to 0.40573 plus 1.38905 times the flow rate. Okay, all right, so again, this is what I really want. Okay, part C says identify and interpret the y-intercept of the regression line. So let's first identify it. The y-intercept is the B0. Maybe I'll even write that down to help you remember. It's the B0, which is 0.40573. So now let's interpret it. Again, I'm going to look at my IS 22 notes here to help me. Turning over to the next page. In part 3, I see my interpretations of the y-intercept and slope. So we say when x equals 0, and we have to put that in context. So let's start with that. All right, so when, all right, our context for x is flow rate. So when, I think we can just say when we have a flow rate, looking at the interpretation up there, when we have a flow rate of 0, what was it? Liters per second. Liters per second. Then what do we say? So when x is 0 in context, the predicted y context is equal to the y-intercept. So the predicted in the y context is the amount of eroded soil. The predicted amount of eroded soil is 0.40573, and what are its units? Kilograms. Okay, so that's interesting. Now let's think about what that really means. If we have a flow rate of 0 liters per second, that means there's not any water flowing at all. So just without water flowing, we're predicting that there would still be this amount of eroded soil, a little less than half a kilogram of eroded soil. And that does make sense in the context of the problem. Soil erodes for other reasons other than just water. I'm assuming, I'm not a scientist. In some cases, the x context being 0 wouldn't make sense, but I think here it's fine. Okay, so then we need to identify and interpret the slope of the regression line. So remember that the slope is the B1 value, and for us, that is the 1.38905. Okay, so let's go ahead and interpret that. So again, I'm going back to my IS number 22 part 3 notes. It says with each additional x context, or I can say something like for every additional unit, whatever that is in context. So let's say with each additional, what would it be? I'm using my x context, so liter per second. For each additional liter per second, right? When I don't put a number in front of the liter, I'm assuming it's just 1. So for each additional liter per second, comma, the predicted y context increases or decreasing depending on whether the slope is positive or negative by the slope. So the predicted to the y context is amount of eroded soil. With each additional liter per second, the predicted amount of eroded soil increases because the slope is positive by 1.38905. And again, I want to put that in context of the units. So amount of eroded soil was measured in kilograms. So for every liter that I add, every liter per second I add of water, the predicted amount of eroded soil increases by 1.38905. I guess I could have said with each additional liter per second added to the flow rate, but I think it makes sense without saying that. So you can leave that in, or you can add that in, or you can leave it out. I think either way is fine. All right, so now we're going to predict the amount of eroded soil for a flow rate of 3.75 liters per second. So remember, whenever we predict, we plug in this value for x, make sure that it makes sense as an x value. Our x values are flow rates, and flow rates are measured in liters per second, so that's fine. So we're going to say y hat is equal to, again, 0.40573 plus 1.38905. But now in place of x, or in place of flow rate up here, we're going to plug in that 3.75. And let's see what we get. Also, as we go to write our answer, we don't want to write y hat. We want to write predicted amount of soil eroded. If you want to, you can leave out predicted and put a hat over the amount of soil amount of soil eroded like I did up here. I just think that looks kind of silly. So I'm gonna go ahead and plug that in. Let's see, 0.40573 plus 1.38905 times 3.75. Okay, I get 5.61. I'm going to go ahead and abbreviate down to round to 2 decimal places because my x value is 2 decimal places. So let's say 5.61. 5.61 kilograms. And then I'm just going to kind of check to make sure that that makes sense in the context of my other sample data. See, with 3.75 as a flow rate fit with 5.61 as amount of eroded soil. Well, 3.75 here. Oh, okay, look, I already have that value. I know it's true amount of eroded soil. I'm guessing the next question is going to ask me to interpret the residual. But 5.61 is definitely greater than the previous one, so I think it does fit with the pattern here. It just wasn't exactly correct. So calculate and interpret the residual. Remember, the residual is the actual minus the predicted. RAP, residual equals actual minus predicted. And that is right here in the part 3 notes, okay? For the flow rate of 3.75 liters per second. So to calculate my residual, I'm going to do the actual. Now the actual value for 3.75, the just y, not y hat, is 6.07. So 6.07 minus the predicted 5.61. See what we get. 6.07 minus 5.61 is equal to 0.46. Okay, 0.46 kilograms, because those again are in kilograms. Now I also, please don't forget, you also have to interpret it. I know a lot of times when it says calculate first, you just kind of only do that and forget to look back at the rest of the question, but it does say interpret. So let's look at the interpretation from our notes. For residuals, it says the actual y context was the residual amount higher or lower. So it depends on whether the residual is positive or negative. In our case, it was positive, and it makes sense. The actual was higher than the predicted. So the actual, let's see, y context. What is our y context? The actual amount of eroded soil is 0.46 kilograms. And again, that's positive, so it's higher than predicted. Higher than predicted for the x value in context that we were given. So then predicted for a flow rate of 3.75 liters per second. Okay. All right, so that is it for the Chapter 10 test review. Like I said, I'm not going to be expecting you to sketch out a scatter plot. You would not do that by hand. Normally, you would use technology to do that. So I'm just going to have you look at the scatter plot and see that it does appear to have a linear relationship, and then use R to determine the strength and direction of that relationship. The scatter plot can also help you see outliers, but again, that's kind of a subjective decision, so I'm not going to be super strict there. Okay, that is it for the Chapter 10 test review. Please let me know if you have any questions. Make sure that you are focusing on those interpretations. Those will be important. Okay,